Hey guys, in this video we're going to be starting out our chemical reactions unit. So today we're going to focus on the parts of a reaction, what they're going to look like, and how to balance reactions. And you may need to turn this up. I do have a slight cold, I'm sorry. I may start coughing in the middle of it, just bear with me. So we have already done types of reactions when we did nuclear reactions, where we were making sure whatever we had on one side equaled whatever we had on the other. So that deals with our law of conservation of matter that says that matter cannot be created or destroyed. It's only going to change from one form to another. Same thing occurs with energy. The law of conservation of energy states that energy cannot be created or destroyed. It's just going to be changed from one form to the other. So whatever we start a reaction with, we're still going to end a reaction with that same amount. So whenever we're writing chemical reactions, you're going to have one or more substances or reactants that are changing into one or more new substances, which are our products. Our reactants are starting materials. Normally they're on the left side of an equation, and products are the resulting materials on the right side of an equation. So for example, when you're baking a cake, the ingredients are the reactants. So that would be the eggs, the oil, butter, flour, sugar, flavoring, depending on what type of cake you're making. And your baked cake will be your final product. One way you're going to see these is as word equations. So for a word equation, you're going to have the names of the reactants to the left of the yield arrow. And if there are multiple reactants, they will be separated by plus signs. And then you're going to have names of the products to the right of the arrow. And yet again, if there are multiples, they will be separated by plus signs. The arrow in the middle is our yield arrow. So this means like reacts to yield, this reacts to give us this, or reacts to produce this. An example is iron and oxygen combine to make rust. So the word equation for that would be the iron plus the oxygen combines to make, that signals us where to put our yield arrow. And rust is iron 3 oxide. Anything that has a common name like that, you'll be given the actual name or the formula for it. Excuse me. Another example is hydrogen peroxide. Whenever you put it on a cut, it bubbles. So hydrogen peroxide reacts to produce water and oxygen. That's what the bubbles are, is oxygen. Different symbols that you're going to see in chemical equations. Plus signs are used to separate two reactants or products. An arrow to the right means that it yields or produces this amount. It's used to separate our reactants and products. Sometimes you'll see a double arrow. It means the same thing, but this is a reversible reaction, so you can flip the equation the other direction. After substances, a lot of times you'll see a letter in parentheses. This is the state of matter that it's in. So S means that it's a solid, L means it's a liquid, G means it's a gas, and AQ means it's an aqueous solution. So it's going to be dissolved in water. A triangle or a delta means that you're adding heat to a reaction. And if you have an element symbol above the yield arrow, it means that you have a catalyst. Another way that you're going to see chemical equations is you're going to have a representation with the chemical reaction where the formulas of the reactants and products are used instead of the names. So an example is our same rust formula. We said iron, which is Fe, plus oxygen. Remember, oxygen is diatomic, so it's O2. Produces the iron 3 oxide, which whenever you write the formula in crisscross is Fe2O3. This is what we call a skeleton equation. It shows the formulas in a reaction, but not how much of each you have. You should add other information to this, including the states of matter of different substances and if there's the presence of a catalyst. So we're going to add the state of matter next to a symbol in the formula to tell if it's a solid, liquid, or gas. So remember, S is solid, L is liquid, G is gas. And some substances will have that AQ, meaning that they are aqueous and dissolved in water. So if we add that to our same rust formula, so iron, metals are going to be solids when they're by themselves, except for mercury that will be liquid, plus oxygen. Most of our molecular compounds will be gases, except for stuff like water that will be liquids. And then the iron 3 oxide, we're going to go over in a later video how you know the state of matter of these ionic compounds. So I'm going to go ahead and tell you that this will be a solid. And if there's a catalyst, so catalysts are added to reactions to speed up the reaction, but they're not actually used up. They don't participate in the reaction. They just speed it along. So these are written as a symbol above the yield arrow, and they're there at the beginning of the reaction and the end without being used up. So this would be if you've ever seen a fight in the cafeteria. There might be someone kind of egging it on, like I bet you won't hit him, I bet you won't do it, I bet you won't do it. They're not actually participating in the fight. They're sitting back and watching, but they egged it on to make it go a little bit faster. One thing where if we're writing formulas is do not forget about your diatomic molecules. Remember, these are very reactive. Excuse me. So they're not found in nature by themselves. They're always found as a pair of atoms. So remember, these are dynamic 7. So you can, on your periodic table, start at 7 and make a 7, and then add hydrogen. We also have the little anagram of Brinkelhoff. So these include nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. And remember, they are diatomic when they are an element by themselves. They are always going to have that subscript of 2. When they are in a compound, you go by normal compound rules. So they don't have to have a 2 whenever they're in a compound. Now we're going to look at how we're going to balance reactions. We're going to go over the rules and then we're going to go through several practice problems together. First, you want to make sure that you have the correct formulas for all of your reactants and products. So this is using all of your nomenclature skills. If your formulas are not correct, your balancing will not be correct. Formulas for reactants will be on the left side of the arrow. Formulas for products will be on the right. You're going to count the number of atoms of each element on the reactant side and product side. And a little shortcut will be if you have a polyatomic ion that appears on both sides of the reaction, you can count it as a unit. Once you've counted all of the atoms on both sides, you can balance the elements one at a time by using coefficients. So remember, coefficients are numbers in front of a substance. You're never actually going to change the formula or the subscripts themselves, only add coefficients in front. I tend to begin by balancing elements that appear only once on each side of the equation, but there's not a set rule for what to balance first. Whenever you think you're done balancing, check that each atom or polyatomic ion is equal on both sides. And then lastly, you want to make sure that all coefficients are the lowest possible ratio. So if all coefficients are divisible by 2, go ahead and reduce it. So let's look at how to balance equations, and we're going to walk through several examples together of how to write these and how to balance these. So look at the first one. We want to write a balanced equation for the reaction between copper and oxygen to produce copper 2 oxide, which is CuO. So copper is Cu plus oxygen. Remember, oxygen is diatomic, so it will be O2. To produce tells us that's our arrow, and it produces copper 2 oxide, which it gave you as CuO. So when we're balancing these, we want to make sure to list out what we have on both sides. That makes it a little bit easier to balance. So both sides of the equation, we have copper and oxygen. On our left side, we have 1 copper and 2 oxygens. On our product side, we have 1 copper and 1 oxygen. So right now our coppers match, but our oxygens do not. So remember, you can only add coefficients in front of a number. So if need be, give yourself spaces to put coefficients in, because those are the only places that you can add numbers. So on our reactant side, we have 2 oxygens. On our product side, we only have 1. So we need to multiply by 2 on that product side, but that coefficient goes in front of the entire substance that has oxygen. So it will go in front. So that does give us 2 oxygens, but that also gives us 2 coppers. So now our oxygens match, but now copper no longer matches. So we have 2 on the product side, 1 on the reactant side, so we also need to multiply by 2 on our reactant side so that everything matches. You've now completely balanced an equation. The rest of this video is just going to be a variety of examples and practice for balancing. For our next problem, hydrogen chloride is an important industrial chemical. We're going to write the balanced equation for the production of hydrogen chloride from hydrogen and chlorine. This one is written strangely, which is why I picked it. So we're going through the production of hydrogen chloride, so that should be on our product side. From hydrogen, which remember is diatomic, and chlorine, which is also diatomic. So if we look at what we have on both sides, we have hydrogens and chlorines. We have 2 hydrogens on our reactant side, 2 chlorines on our reactant side, and 1 of each on the product side. So in order to balance, we need to multiply by 2 on our product side, which will give us 2 hydrogens and 2 chlorines, so that everything matches. Let's look at some more examples. In our next one, we have hydrogen peroxide, that's the H2O2, producing water and oxygen. So on both sides of the equation, we have hydrogen and oxygen. On our reactant side, we have 2 hydrogens and 2 oxygens. On our product side, we have 2 hydrogens, but here we have a total of 3 oxygens, 1 from the water and 2 from the oxygen. So here's one thing that comes up that's tricky. Our hydrogens match up, but our oxygens do not, and we cannot multiply the 2 oxygens on the reactant side by anything to make it equal 3, because we can only add whole number coefficients. So we need to get rid of that odd oxygen that's on our product side, which is in water. So in order to get rid of an odd number, you multiply by 2. So that will give us 4 hydrogens. And if you count our oxygens, there are 2 in water and then 2 in oxygen for a total of 4. So now, to make this match up, we can multiply the hydrogen peroxide by 2, giving us 4 of everything. So if you come across a problem where you have an even number that can't equal an odd number, make that odd number even by multiplying that odd one by 2. Let's look at the next one. We have magnesium and hydrochloric acid producing hydrogen magnesium chloride. On both sides, we have magnesium, hydrogen, and chlorine. On our reactant side, we have one of everything. On our product side, we have 2 hydrogens, 1 magnesium, 2 chlorines. So magnesiums match, so let's look at hydrogens. To make them equal, we need to multiply by 2 on our reactant side, which gives us 2 hydrogens and 2 chlorines, so everything is balanced. Let's look at our next example. We have ethylene, which is C2H4. Anytime you have something weird like that, you'll be given the formula. Burns with oxygen, so remember oxygen is O2 because it's diatomic, to produce carbon dioxide and water. So if we list what we have on both sides, let me scroll down a little bit. We have carbon, hydrogen, and oxygen. So one thing is whenever you only have carbon, hydrogen, oxygen, I recommend balancing the hydrogen first, then the carbon, then the oxygen. And one thing is hydrogen can have no odd waters. That's going to give us that even number of oxygens that we need at the end. So count up what we have on both sides. We have 2 carbons, 4 hydrogens, and 2 oxygens, compared to 1 carbon, 2 hydrogens, 3 oxygens. So if we do the suggested order, let's look at hydrogen first. We have 4 hydrogens on the reactant side, 2 on the product side, so we need to multiply by 2. That's not an odd number, so that's okay. So that gives us 2 hydrogens. That gives us 2 oxygens in water, plus the 2 in carbon dioxide for a total of 4. Now, oh excuse me, that should be 4 and 4. So hydrogens are matching. Now fix carbon. We have 2 on the reactant side, 1 on the product side. So we need to multiply by 2. That does give us 2 carbons, but that also changes our oxygens. So we have 4 in carbon dioxide plus 2 in water to make a total of 6. So now to make oxygen equal, we need to multiply by 3 on our reactant side for everything to be balanced. If you came across and we're supposed to put an odd number in front of water, go ahead and double it. That'll make it easier to balance in the end, and you don't have to go back and forth as much. Let's look at our last couple of examples. So the one up top, we have silver nitrate and hydrosulfuric acid producing silver sulfide and nitric acid. This is one where I said if you have a polyatomic that appears the same on both sides, you can leave it as a unit and you don't have to count them separately. So that may make it a little bit easier when you're balancing. So on both sides we have silver, we have nitrate. Remember that the 3 is part of nitrate, not a subscript. We have hydrogen and sulfur. So on our reactant side, we have 1 silver, 1 nitrate, 2 hydrogens, and 1 sulfur. On our product side, we have 2 silvers, 1 sulfur, 1 hydrogen, 1 nitrate. So pick anywhere to start. I tend to start at the top. So I'm going to go with silver first. So in order to make my silvers equal, I need to multiply by 2 on my reactant side. That gives me 2 silvers. That also gives me 2 nitrates. So now silver matches, but nitrate does not. Since I have 2 on the reactant side and 1 on the product side, I need to multiply by 2 on my product side. So that gives me 2 nitrates, and it also gives me 2 hydrogens. And if you look, everything is now balanced. So it's a little bit easier than counting all of the nitrogens and oxygens independently. Let's look at our last example. We have zinc hydroxide, so zinc and hydroxide. Remember, zinc is a positive 2 charge, while hydroxide is a negative 1, so it'll be ZnOH2. Combines with hydrogen phosphate. Now hydrogen is a positive 1 charge, phosphate's a negative 3, so it'll be H3PO4 to produce zinc phosphate. So remember, phosphate's negative 3, while zinc is a positive 2, and water. So I'm going to scroll down so I can list out my elements because I don't think I can do it up top. So here, hydroxide does not appear on both sides the same, so we will have to separate it. But phosphate is the same on both sides. So we can keep that together as a unit. So on both sides we have zinc, oxygen, hydrogen, and phosphate. Sorry, that's a P. So on our reactant side, we have 1 zinc. The oxygens, we want to make sure not to include the oxygens that we're counting as part of phosphate. So we have 2 of those. For hydrogen, we have 2 hydrogens in zinc hydroxide plus 3 in hydrogen phosphate for a total of 5. And we have 1 phosphate because remember that 4 is part of phosphate, not a separate subscript. On our product side, we have 3 zincs, 2 phosphates, 2 hydrogens, and 1 oxygen that's not part of phosphate. So we got a lot of work to do on this one. So let's start with zinc. We have 3 on our product side, 1 on our reactant side. So we need to multiply by 3. So that does give us 3 zinc, but that also alters our oxygens and our hydrogens. So the coefficient and the subscript multiplied together. So oxygen, we have 6. For hydrogen, we have 6 in zinc hydroxide, plus the 3 from hydrogen phosphate for a total of 9. So zinc matches right now. So let's look at oxygen. And remember, this is oxygen that is not in phosphate. We have 6 on the reactant side and only 1 on the product side. So we need to multiply by 6. So that gives us 6 oxygens. And now that gives us 12 hydrogens. Now, hydrogens are a little bit funky because they're in both substances on the reactant side. So I'm going to skip and go to phosphate and see if it fixes my hydrogens for me. Since I have 2 phosphates on the product side and 1 on the reactant side, I'm going to multiply by 2. So that does give me 2 phosphates. And if you look at your hydrogens, we had 6 hydrogens in zinc hydroxide, and now we have 6 in hydrogen phosphate for a total of 12. So we're completely balanced. Make sure that you're practicing these, and it does help to list out the elements themselves.